Previously, we developed confidence intervals associated with the two parameters of our regression line, beta naught, beta 1. We also did hypothesis testing on those two. What we're going to turn to now is a confidence interval on the mean response. It's a slightly different type of thing, and you'll see the result here for our aquifer data represented by these two dashed lines above and below our condition mean response. Right? And these are, the one demonstrated is the 95% confidence interval. One of the things to take note of is how these two dashed lines are actually curved away from the regression line as the further away they get from the mean. We're going to see that as we go along. And the way we're going to develop that is to think first about the expected value of the function given in any particular x value, right? And given our line that we have, then the expected value y given x0 is going to be equal to beta naught plus beta 1 times x naught. Remember, x naught is the conditioned value, right? Also keep in mind that although this is the true statement for the population here, that when we went to go estimate our parameters, we looked at beta naught being equal to y bar minus beta 1 hat times then x bar, right? So that when we come in to take a look at the estimated value of the mean, the conditional mean, this is what we're going to estimate now. This is going to be, once we substitute in these values into here, right, beta naught expression goes into here, and then that becomes beta 1 collect terms, we get y bar plus beta 1 hat times xo minus x bar. Right. And so the other aspect of this that'll be important is now we have an expected value for y given x naught, and we also though need to go find out what the variance of mu hat y given x naught is going to be. Right? And this actually isn't too difficult to go figure out. We're going to substitute in for that expression and get y bar plus beta 1 hat times x0 minus x bar. Right? Now, it'll turn out that, remember, variance of a sum is equal to the sum of the variances if we include the covariance appropriately, right? So this will become variance of y bar plus the variance of this stuff. But this is a constant now for specific data, right? So this becomes the variance of beta 1 times this. If it's a constant, it gets pulled out and it gets squared in that variance expression. And what I haven't written is any covariance term. And it turns out covariance of y bar and beta 1 is equal to 0. You can kind of see that. I'll just kind of hand wave this. This y bar, of course, is the sum of the y's over n. And remember that beta 1 is equal to sxy over sxx. So there's nothing but x's here, and this is the sum of x times y minus n times x bar times y bar. Right? So there's a lot of x's running around here. So part of that lack of covariance makes sense, but there are some y's that are running in there, and that might seem a little head scratcher about why this turns out to be, and we're not going to demonstrate it. We're going to take it on faith that it really is for this particular development work. Okay, and then the next part here then is that the variance of y bar, remember that's back to our original variance divided by n, right? Sample statistic, sample and the mean there, and then the variance of beta hat is back to sigma squared over s xx, and then of course we still get this. Right, and really, this is that variance of the error, right? Because that's where, after we take away the regression, the leftover remaining is coming from the errors or the residuals, right? And we can of course factor that then on out, and we get 1 over n plus square of that difference all over sxx. Okay, and just for purposes of shorthand notation, let's call that the variance associated with this conditional mean, and I'm not going to write out the rest of the subscripts there, just to kind of keep it a little bit short and sweet and simple. Right, and actually that should be sigma. And then remember, what we so often do is say, well, we don't know those population values. Instead, we'll substitute in and substitute in. And this is all just functions of x over here, right? And we've already calculated this. And of course, if we want the standard deviation of that, then we just take the square root of all of this. So get rid of that and take the square root of that, and that's going to be t distributed with n minus 2 degrees of freedom when we go and we develop our confidence interval, right? So our conditioned mean of y given x naught is going to be, our confidence interval will be plus or minus the t critical value, t alpha 2, and minus 2 times then that standard deviation. That's why I wanted to use the shorthand notation, so I would keep this nice and simple like we've seen it before. This is really mu sub, right? Gets really down deep in there, and that's this guy right there. And that's what gives you then the confidence interval on the mean response. Now note something in two aspects here that are crucial here. That we have 1 over n, so the larger our sample size is, then the smaller then the bound is going to become. And then the other aspect is that the further away we are from the mean of the independent variable, then the larger this is going to become. And that's why you see these curves flare out as opposed to being just parallel to our regression line.